I'm going to do something a little different with this talk, and I'm going to try not to be too technical, so I'm going to kind of also say what the point is right away. This is a workshop on the foundations of routing. We're all interested in routing. Routing is great. One of the few things I like more than routing is network design. So I'm going to try to turn routing into a network design problem. That's kind of the point of this talk. And this involves kind of rethinking of what we mean by routing. And so that's hopefully going to be kind of the foundations, is what I mean. Also, I should say this is joint work with a bunch of Hopkins people, together with LTN, which is a company founded by some Hopkins people, and Amy Babet, who did most of the work on this, to be honest, just today signed a job offer at the University of Pittsburgh. So she's going to be a professor at Pitt now, which is very exciting. Right. Also, this workshop is funded by the NSF under AITF. This work is really growing out of an AITF grant, so I thought it was also very appropriate to talk about here. We kind of wrote this grant, and this is two of the papers that came out of this, which are kind of related and about this topic. So one of the other different things I'm going to do in this talk, hopefully, is I'm clearly like a theory person, but instead of giving a pure theory talk, I'm going to try to give like a half systems, half theory talk. It's not clear that I have the ability to give a systems talk, even half of a systems talk. But I'm going to try to do my best, and we'll hopefully answer any questions you have. OK, so good. What's our setup? Our setup is we're going to try to do things across the internet. Like natively across the internet, we can have high reliability, like TCP more or less gets us this. Or we can just kind of use UDP, and similar things just kind of like spew out packets and hope that things work. Right? This is kind of what's built into the internet. But what we want are some applications that we need to be kind of super reliable and like super fast. So in fact, one of the other ways I'm going to be different than most of the talks today is I'm not really going to care about congestion. I'm going to care about latency. So it's a little bit of a different setting. So I'm going to talk about these applications more in a minute. But for now, you can think of broadcast quality TV, but there's other things. Right. So in particular, one of the things that LTN does, so the company that we work with, the way they make most of their money is that CNN gives them a ton of money in order to do live video conferencing on TV. Right? So you think CNN is trying to interview someone across the country. You want this to be real time, right? You can't have lag. You can't have errors. This has to just kind of work. And it has to feel like it's real time. So you can't just like use TCP to send data, right? Like that's not good enough. So LTN built this overlay network, which I'll talk more about. And the service they provide is this kind of very fast, very reliable video conferencing. OK, good. Is this dying? OK, so here's another thing. So I'm at Hopkins, as we said. So one of the kind of pseudo-obligatory things when you're at Hopkins is you at least pretend to be interested in medicine. So we're really going to be motivated by this remote robotic surgery. Right? This is actually what we're going to try to do. So think about it this way. There's a surgeon at Hopkins. And he's the best surgeon on Earth because he's at Hopkins. And they want to operate on someone in California. Right? So the vision is that they'd have this little kind of machine that they put on the goggles, they put on some hand things, and they kind of act like they're doing surgery. And this robot on the other end actually does the surgery. Right? So this is the goal. And here, kind of the demand, we have very extreme demands. So to see this, why is this not working? Okay, so here, for live video conferencing, your kind of 200 millisecond one-way delay is kind of what the human perception is of like, this is reasonable, and I feel like I'm in real time. So for this robotic surgery, somehow our fingers are faster than our eyes. Apparently, this is a thing. So if I have a glove on, and I'm getting kind of haptic feedback from this robot on the other side of the country, I need to get 130 millisecond round-trip delay in order for me to feel like I'm actually there. Okay, so this is hard. We have 80 millisecond of round-trip propagation delay because of the speed of light. Okay, so that gives us like very, very little time to play with to run fancy recovery protocols or routing protocols. Like we just don't have time to do anything fun, which is unfortunate as an algorithms person. I like having time to do fun algorithms. But OK, that's the world that we're going to live in. So Right, we can't, LTN is not, Google or Level 3 or AT&T. We can't mess around with what's going on in the actual internet. What we can do is run a overlay network, right? So this is kind of familiar to probably everyone here, right? I have all these cities. I kind of rent out space in a data center, and in all of them, I stick my computers on them. I connect them to a bunch of different, maybe, Level 3 and AT&T and someone else, and I do all this stuff. And now I have my own network running on top of the internet. And right, so I can control what's going on this network. Right, so that's the kind of the key point here. Good. So here's the key idea. Like I said, here's why I'm going to try to change routing into network design. All the talks today, routing has been about paths. I'm going to send along this path, or that path, or multipath, or oblivious path, or it's all paths. I want to get away from paths. I want to think of routing as being subgraphs. Okay, so this is the kind of core idea that we're going to use, that because we're running an overlay, we can do fun routing things. And in particular, we can route along subgraphs, which we call dissemination graphs. And this is going to be enormously helpful to us. Like intuitively, what's this going to let us do is we're going to say, well, here's an area of our network that we think is problematic. Right? Well, if I think it's problematic, I might want to run like 5 disjoint paths or something like this. But if it's only that area, I can run kind of one disjoint, one path up to that area, then split into 5 paths, and then recombine later. That's kind of intuitively what's going to go on. Okay, so our routing isn't really paths. It's choose a subgraph. For that subgraph, the edges in that subgraph are the edges that we forward our packet along, right, for all packets in the flow. So what's the cost of this? More or less the number of edges in the subgraph, right? It's not exactly true, but in an overlay, we can think of sending from one node to another has some fixed cost. So the cost of some routing subgraph is just the number of edges in it. So the question here, of course, is now, how do I choose this subgraph? Right? What should I do? OK, so let's think about this for a minute. Let's draw some pictures. So this is kind of a subset of the LTN network. So if I do disjoint paths, suppose I'm trying to send from Washington to LA. I want to be robust to 3 failures or to 2 failures. So I run 3 disjoint paths. There's 1, there's 2, there's 3. Fine, right? That works. It's a pretty good trade-off between cost and reliability. Unfortunately, it kind of has this uniform investment across the network. The other extreme, and so think like robotic surgery, right? Like, what is your failure case, right? Robotic surgery, the failure case is you cut someone open, the network goes down while they're bleeding out, right? Like, this is a bad failure case, okay? So, I might want to invest enormous amounts of money to make sure that that doesn't happen, right? If I'm willing to invest enormous amounts of money, then what am I going to do? I'm going to send a copy of every packet on every edge in the network that could conceivably get there in time, right? Like maybe I don't send it over to London and back, because even if everything works perfectly, that's too long, right? So we call this time-constrained flooding. I'm just going to send every packet on every link that might conceivably help. Okay? So if I really don't care about money, or I really care about not failing, this is what I'm going to do. Yeah, just one. Because, in fact, so LTN actually made it, what it really does is it, for video, it runs very fancy video-optimized recovery protocols. So we're not going to do that. Well, that's an interesting future work is for robotic surgery, can you design specialized protocols? Yeah. So that's one extreme. So we're going to, in some sense, try to live between these 2 extremes. Right, so can I use knowledge of the network characteristics to do better? Finding a better one. OK, so we want to find the best trade-off between cost and reliability subject to these very strict time constraints. Cost is the number of times a packet sent, which is basically the number of edges used. The reliability is the probability that I make it there within some time bound. Right? So as has kind of come up a couple times, like Ava mentioned this and we mentioned this at our table earlier, kind of computing network reliability is sharp p hard. That introduces some annoyingness that I'm going to get rid of, and we can talk more about that later. Good. And there's obviously kind of two problems here, right? Like, I could say maximize my reliability subject to a budget constraint, or minimize the cost subject to a reliability constraint. Right? Both very obvious, reasonable problems. OK, so I should say, like, we started out thinking about this in a probabilistic way, because that seems like what you would expect to do. It turns into a really hard problem. There's a bunch of really interesting open theory problems that I'm interested in attacking, but I don't actually know how to solve right now. So what we're going to actually try to do is take the probability out of it, unlike what Manya was talking about. So right, we're going to try to look at previous data, figure out what kind of problems tend to happen, and figure out what are the good dissemination graphs for those kinds of problems. Yeah?
This is a bit of a tangent, and possibly you won't know the answer. What is the propagation delay of the devices in your overlay, in particular if you're doing replication? That I don't know the details here, but it might cost more than just doing some.
Totally. So because not only do you have to make copies of it, you have to kind of recombine later, right? You can imagine this being like incredibly expensive and using up your entire time budget just in that, right? That's a great question. Yair's lab built this open source overlay messaging toolkit called Spines that does this apparently insanely fast. I don't know how they do that. There's a different series of papers that do that. We just kind of use Spines as a black box, and it works. Like, it works very fast.
So for the graph, though, like if you're going across the US, I can imagine that you only really can do paths of maybe 2 or 3 segments.
Yeah, pretty much. I would think that's true. And you can only do paths of 2 or 3 segments, and you can't do any fancy recovery protocols, or like you just have to spew packets and hope that they get there. But yeah, you certainly are not doing like 8-hop paths across the US. Which is why Yair has a whole different talk/rant about how we don't need to ever consider networks of size bigger than like 15 or 20, because that's all that you can do. Which again, as someone concerned with asymptotic algorithms, is not really what I like hearing, but good. So what did we do? So right, luckily we were working with LTN. We just kind of got a bunch of data about their network and how often things went down and what these failure events looked like. And then we built a simulator. This doesn't, we couldn't just use NS2 or NS3 because we have our own thing, so whatever. We had a master student build a simulator, which was awesome. And we kind of realized a couple things. So first, 2 disjoint paths is pretty good most of the time. So again, like most of the time, meaning 99.99% of the time, or 99.9% of the time, 2 disjoint paths is doing totally fine. Right? You're not seeing big failures. When it doesn't work, what's going on isn't so much that like somewhere in the middle of your network there's a big correlated failure. Right? That's not what seemed to happen. What seemed to happen is that something crazy was going on at the source that was causing like massive issues right around the source, or something crazy was going on at the sink, causing massive issues right around the sink, or both. It wasn't really a middle of the network problem. Maybe that's because our network only had 20 nodes in it, and there is no such thing as the middle of the network when you only have 20 nodes. But OK, what we saw is that there's kind of these weird, we don't even know how to characterize them, but just like crazy things at the source, crazy things at the sink, crazy things at both. And that's when 2 disjoint paths doesn't work. OK, so then what did we do? We kind of, for every possible flow, for every source-destination pair, we compute 4 graphs, right? These 2 disjoint paths that we're going to run on most of the time. Then if we detect a problem at the source, we have pre-computed this kind of dissemination graph that's robust to source failure, right? And then if we detect a problem at the sink, we have pre-computed a dissemination graph that's kind of robust to sink failure. And then if we detect problems at both, we have pre-computed a dissemination graph that's robust to both of them. Now again, like lots of interesting systems question here is about how do you actually detect these quickly and do quick failover, and that's in our paper, and I don't honestly know the answer to that, but presumably I could find it for you. That's what we do. OK, so the point is that we pre-compute these kind of 4 graphs for every flow, and when we detect failure, we switch over to the appropriate one. OK, now this is still kind of oddly, yeah?
Couldn't you just run the one that's robust to both source and sink failures all the time, right?
You totally could. It would just be expensive, right? So the cost of this is kind of how many times do I have to forward a packet, right? So the more robust I am, I could do this flooding all the time, right? Like it works. It's just very expensive. But yeah, if you're not so concerned with money, but you want to be a little bit cheaper than time-constrained flooding, just using this all the time might be an actually reasonable thing to be doing.
Yeah. Just another question. You have those disjoint paths logically, right? Because you have an overlay network, right? So the two disjoint logic paths, they actually might not be physically disjoint.
Absolutely.
So there might be some common mode failure. So do you address this? No?
Yeah, so that's a great question. I kind of came in, I guess, assuming that because we're in an overlay network, there's all sorts of weird correlations that we don't know about because they're going on underneath. It just didn't seem to actually be what was happening. There might be all these correlated failures, but when we run two disjoint paths, again, it works unless something is going wrong at the source. Maybe that thing going wrong at the source is that there's some failure on level 3 and a lot of stuff is correlated along that. Kind of could be. Like, we're not really characterizing this going wrong at the source, what that actually is. That's a whole bunch of different things that might be going wrong. But yeah, I mean, you're totally right. These are logical links, right? They're not physical links. And so things are disjoint that might not actually be disjoint. But you can imagine they're disjoint at the cities level, right? So you're kind of unlikely to share too many edges if you're routing kind of through the south and through the north, right?
Sometimes you do certain different providers, but they actually use the same underlying conduit or something.
Yeah, totally. It's a totally reasonable question. We didn't really kind of explicitly think about that because it didn't seem to be what was showing up in our data. But as you scale this up, I would think that would show up more and more and more. OK, so this is the obvious question now is like, I've said we're going to build these graphs, but like, what should these graphs be? I've even said what I want them to do, but what should they be? So okay, let's think about this for a minute. Let's think about Atlanta to LA in this graph. So two disjoint paths, like fine. Through Denver, through Dallas, I have my two disjoint paths. What should I do if I have a problem at the source, at Atlanta? So again, like, I just have this weird undefined problem. I don't know what it is. Something is going weird at the source. So I claim the obvious thing to do is send a copy of the packet from the source to all of its neighbors, because you don't know what's going on. Right? So you just want to maximize the probability that something gets through. So you send from the source to all of its neighbors, but now you're in this setting where the problem is at the source. There really aren't problems going on inside of the network. So you send data to all of the neighbors of the source, and then from each of them, you just try to get to LA. And now you're not so concerned with fault tolerance anymore. OK, does that like intuitively make sense as like an approach to trying to do this? Not the only possible approach, but an approach. OK, similarly, if I have a failure at the sink at LA, I'm going to kind of try to pull in my packet from all of the possible neighbors. Right? So I look at all the neighbors of LA, and I say, well, something's going on, but I'm going to try to get the packet to all of these. And then hopefully one of them will be able to actually get it through to LA. So I'm trying to send out from Atlanta to like all of the neighbors of LA, and then hoping that one of them gets through. OK, so like, what is that problem? Let's put on our theory hats, or at least our defining problems hats. Right, suppose I have this failure at the source thing. Right, so S is my source. I have a latency bound L. I have some kind of weird faults going on around the source. So let's make a simplifying assumption that the distance from the source to all of its neighbors is the same. Not true, but close enough maybe. And we can actually handle generalizations of this. This is just to show the basic setting. So if I make that assumption, what's my remaining problem? My remaining problem is build paths from these nodes, the neighbors of the source, to my sink, minimizing cost, subject to the length of those paths being, at most, my remaining time bound. Okay, that is the remaining problem. This is basically, you could think of this as Steiner tree with length bounds. Right? Like at Steiner tree, you have to connect my root, my sink in this point, to all of these terminals. I can go through Steiner nodes. It's Steiner tree, I just have a length bound. That problem is called something. It's called shallow light Steiner tree. Guy Kortsarts, Mohammad Taji Hajigai, a few people have a bunch of papers about this problem. Good, shallow light Steiner tree. So I'm going to talk more about shallow light Steiner tree from a theory point of view in a minute. But let me point out something now which I'll point out again later, that obviously this is NP hard, okay? The number of neighbors of a node is kind of small relative to the size of the network, right? Like presumably these nodes have degree, I don't know, 8, 5, 10, somewhere around there. My network is growing, it's big. So there's this notion of a fixed parameter tractable algorithm. This is what we're going to be using later, where I'm going to allow myself to spend time that's exponential in this number of neighbors, because I expect that to be small, as long as I'm polynomial in the rest of n. Okay, so this is not, in the kind of theory worst case, if I am connected to everyone, kind of, right, my neighbors has size n, this is an exponential time algorithm. On the other hand, if I have 10 neighbors, like 2 to the 10th is a totally reasonable constant to have in front of your running time, right? N to the 10th, not so much of a reasonable running time, right? So we're going to kind of be living in this called fixed parameter tractable algorithms, which I'll talk more about when I get to the theory part of the talk. OK, good. So that's how we handle the source failures and the sink failures. What about both? Well, you do kind of the obvious thing, right? I look at all the neighbors of Atlanta, all the neighbors of LA, and I say, there's problems at both. I have no idea which of these are going to get through. So I kind of need to connect all pairs of them. Right? So from a theory point of view, right, I have Atlanta, I have LA. Look at all my neighbors of Atlanta, all my neighbors of LA. There's something weird going on here, something weird going on here. So I send this packet. I have no idea which one of those is actually going to get through. If I send packets from this set to the sink, I have no idea which ones are actually going to get through. So I kind of need to connect every node here to every node here within my length bound, in order to guarantee that I actually do get my packets through with the right time bound. Right, so this is kind of Steiner forest or Steiner network. But the demands here are a complete bipartite graph. And I have a length bound. So this is some kind of, from a theory point of view, this is what's called the shallow light Steiner network problem with a complete bipartite graph as your demands. Right, so basically I say, here's my neighbors, here's my neighbors. Now I can forget the original nodes, it's fine. I just need to create as cheap a subgraph as I can that has a path from every node here to every node here within my length bound. Right, that's the theory problem. That's the algorithms problem. So good. Are there good algorithms for this problem? Good. So we got a bunch of data somehow. Thankfully, Yair's lab did all this work. I don't know what they did, but they got a bunch of data from LTN and did a bunch of analysis and simulated what kind of would have happened if we had done each of our different things. And here's what we get. I'll show 2 slides on kind of evaluation. So one, if I do this time-constrained flooding, that's kind of the best I could hope for in terms of reliability. Right? So that has kind of super high reliability, whatever, some unavailability, 1.46 packets lost per late per million, fine. If we do this dissemination graph approach and we choose appropriate dissemination graphs, then we see very similar numbers, right? 1.52, about the same number of 9s here. It all looks about the same. Compared to if I do just like 2 disjoint paths static, or even if I allow dynamic 2 disjoint paths. So I kind of have 2 disjoint paths, but I kind of choose them. I respond to failures and reroute appropriately. Or a redundant single path. Like kind of all of these have noticeably worse reliability. Okay, so I'm not comparing to every possible thing. All I want to say is that we're doing similar to the best possible thing. And other obvious approaches are doing noticeably worse. OK, but maybe that's just because we chose very expensive dissemination graphs. I'm going to argue that that's not true. Right? So here's, how do I read this? Look at the gap between single path, which is the least fault tolerant, to this time-constrained flooding, which is the most fault tolerant. Right? So think about that performance gap in terms of reliability. So normalize around that. We'll call this 0%, that 100%. We get 99.8% of the reliability. And our cost is only kind of 2 times the cost of the single path. Okay, so if I did full time-constrained flooding, I'd get my best possible performance, but it cost me 15 times what a single path would cost me. I'm getting almost that whole way there at twice the cost of a single path. If I did, let's say, static 2 disjoint paths, I'd pay 2 times, because it's 2 disjoint paths, basically. A little more, because one of them is not necessarily shortest. But I only get 50% of the reliability, 50% of the gain. Okay, so hopefully this is my convincing systems people that this works. I don't know how convincing this is, but hopefully I can answer any more questions you have about the evaluation. What was the average degree? Good question. I don't know. Around maybe 5-ish. So the cost is affected by certainly the cost of time-constrained flooding is affected by the average degree, right? The cost is affected by how many edges I choose in my graph. So if I choose a lot of edges, I could have a very high degree graph, but choose very low degree solutions, right? And then it's not a function of my degree. If you're asking what's the average degree in the graphs that we pick, the average degree is relatively small, yeah. The max degree is very high, right? Because we're targeting the redundancy at the source or at the sink. So there is some node that has massive degree. But everywhere else, it's very small. Okay, good. So I'm going to move to theory mode for a little bit. Good, so back to theory. So, right, I actually kind of swept this under the rug. I didn't really say how we picked these things. I said, we solved this problem, right? Okay, well, that's an algorithms question, right? How do we solve this shallow light Steiner tree or shallow light Steiner network problem? And from a theory point of view, what about other classes of demand graphs? You can imagine other networking scenarios where I know more about the faults and I have some demand graph that's not exactly one of these. We didn't really concern ourselves with this, but it's interesting. Weak approximation algorithms are kind of not super useful, right? It's very common to give 3 approximations or 4 approximations, but I can get 15 times. I can get a 7 approximation basically by just running this time-constrained flooding on the graphs that we cared about. So I want very, very good approximations. But as I said before, I don't really expect the demands to be that big, right? Because it's just like the number of neighbors of some fixed node. So I'm going to be happy with running times that are kind of some arbitrary function of p, the number of demands. So this is the number of neighbors of my nodes, as long as you're polynomial in n. And in theory, I'm really allowing an arbitrary function of p. This could be 2 to the 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 p. I'm not going to do that. The worst we're going to give is 3 to the p. But from a theory point of view, that's what I'll allow. OK. Good. So for the tree case, so for star demands, right? Think of this is the shallow light Steiner tree, right? My demands are a star from the sink to all the neighbors of the source. It turns out, for reasons I'm not going to go into, because a lot of people here aren't theory people, and I don't want to bore you, that having length bounds is kind of morally similar to having directed graphs. You can do a kind of layered transformation, and things work as long as you have star demands. This all works out fine. So what this means is I can take an FPT algorithm for the directed Steiner tree problem, which exists, and I can just use that for a shallow light Steiner tree, right, via this kind of relatively standard transformation that's not super interesting, so I'm not going to spend time talking about it. I'll say directed Steiner tree was one of the first problems that people developed fixed parameter tractable algorithms for. This is Dreyfus and Wagner in the 70s. So this is a classical FPT algorithm. With general demands, including bipartite demand, this complete bipartite graph, it's actually not the case that length bounds are kind of similar to directed graphs. This reduction breaks down. So we need to kind of directly reason about length bounds rather than going through this directed setting. OK, so let me just kind of state the results. So I'm going pretty fast. So that's good, because I guess we're running a little behind, so I'll end a little early, and we'll have time for discussion. OK, so here's our kind of theory results. Let C star be all star graphs. Let C lambda be all graphs that have at most lambda edges. Think of this as a constant. So these are constant size graphs. And I define this problem SLSNC to be the shallow light Steiner network problem where all my demand graphs are in that class. Right? So SLSN of C star is exactly shallow light Steiner tree. SLSN of complete bipartite graphs is exactly the problem that I care about for this overlay dissemination graph problem. But you can generalize this. Okay, so assuming unit edge lengths, which is not true, so I'm going to talk about the general case later. But for now, assuming unit edge lengths, we have these matching theorems. So if there's some constant lambda, so that my class C is a subset of stars and constant size graphs, then I have an FPT algorithm. Otherwise, it's what's called W1 hard. This is like the equivalent of NP hard for fixed parameter tractable. Right, so this is like a really harsh dichotomy theorem. Like if you live within this class, you have good algorithms. If you're anything else, then you don't have good algorithms. Okay, so similarly, yeah.
That's the problem of exactly solving? Or
This is the problem of exactly solving. Absolutely. We're going to talk about approximations in a minute. But yeah, this is for the problem of exactly solving. OK, so if I have arbitrary edge lengths, which is the more realistic kind of setting, then my life actually becomes difficult. There's no FPT algorithm possible even for a single demand. If you think about it for a minute, you see this contains what's called the restricted shortest path problem, which is NP hard. So I can't do this. But maybe what I can do is find approximation algorithms that run in this FPT time. Right? This 2 to the number of demands times a polynomial in n. Maybe I can give a very good approximation algorithm for that. In particular, restricted shortest path has very good approximation algorithms. But here again, what we find is this dichotomy. So if you're one of these easy classes, you're all stars together with a constant number of things, then great. I can give you a 1 plus epsilon approximation in FPT time, right, for as small epsilon as you want. If you're anything else, then you can't do a better than 5/4. So there's a lower bound of 5/4 on your approximation. Okay, so you might 5/4 still is pretty good. This doesn't rule out like all kind of good things, but you can't get this 1 plus epsilon. Right? You certainly can't do better than 5/4. Okay, so I want to good. So I hate having slides that just throw up theorem statements, so I want to kind of show some pictures. Because I find this theorem like really crazy when you think about what it means. Right? So what it means, if you think about both of these, both the unit edge length and the non-unit edge length, I have easy graphs and hard graphs. Right? Easy is stars and constant things. Hard is everything else. Great. So like here's an easy graph. That's hard. That's hard. That's hard. Right? Like a star with one edge is not a subset of stars and constant size things. Right? So all of a sudden, I take this graph, which is easy. This demand graph is a star. And I add in this one extra demand, which doesn't even touch them. And now all of a sudden, there's no 5/4 minus epsilon approximation. Like, I find this incredibly counterintuitive. It's how is it possible that this is easy and that's hard? But yet, that's the case. Good. So right, I want to compare and contrast this a little bit with this directed thing, right? Because I said that for arbitrary demand graphs, directed and length-bounded are not kind of the same. They're different. For a directed Steiner network, so that's the problem. There's not particularly good approximations, but this is the best known, a SOTA paper from myself and a few people a few years ago. This is a hard problem. But Feldman Marx, so we take inspiration from this like really, really amazing paper by Feldman and Marx in iCalc 2016, where they gave this very similar kind of easy-hard dichotomy for FPT algorithms for a directed Steiner network. What's their theorem? It's a little more complex. So I look at these graphs, which are called lambda caterpillars. So think about this as just like, it's called a caterpillar because it looks like a caterpillar. I've got this backbone of length lambda, and off of it I have what they call hairs. I would call them legs, whatever. So from each of these nodes, I can have a star out of it. And then I have this path as a backbone of length lambda. Okay, that's what a lambda caterpillar is. So they define C lambda delta to be all graphs where I can delete delta things from the graph and be left with something which is transitively equivalent to a lambda caterpillar. So what is transitively equivalent? Because it's a directed graph. Let's not worry about it. More or less, it's just saying that if you can delete a few edges and still be a caterpillar, that's what C lambda delta is. Okay, and their theorem is that this is the class of easy graphs for directed Steiner network. Right, so for them, if you're in C lambda delta, then directed Steiner network on that demand class is in FPT. Otherwise, it's W1 hard. Okay, so I want to contrast this with what we have for a shallow light Steiner network. Right, so our like star with one edge hanging off it. Right, that's a one caterpillar, and I have to delete one. Sorry, I have to delete one edge just to make that a star. Right, and a star is a one caterpillar. So a star with one edge hanging off it is in C11. Right, so that star with an edge hanging off it is easy in DSN. It's one of the easiest things that there is. It's 1, 1. But for us, it's going to be hard. So what does that mean? Like for us as algorithms builders and hardness provers, this means that it's going to be harder for us to prove hardness, right? Because more things are hard. So my reduction has to handle this much wider class of demands. The flip side, I'm trying to design algorithms. I only need to design algorithms for stars, right? More or less, because everything else is hard. And algorithms for stars, that's shallow light Steiner tree. Like I said, we already know how to do that. Okay, so I'm clearly losing the interest of all the systems people. So I'm going to wrap it up and say, how do we prove this hardness? Just like one slide. We kind of prove this lemma, which says that if you're not in this class, you must have one of the following structures. Then we say, and one of these structures is, in fact, a complete bipartite graph. And then we say we prove a reduction from the multicolored clique problem to each of those structures. And that gives the proof. And it's kind of highly technical. I have other slides that I'm maybe not going to show, which kind of give the, the slide of the scary theory picture, right? With the picture of all like this reduction and how all these gadgets fit together, and it's a mess, but you can do it. Okay, but let me not do that. Let me just say that the message I want to get across here, right, is that if we're talking about foundations of routing, we should think about whether we need to actually think about paths, right? Like, I think most of the time paths are good, right? Like, I'm not claiming by any means that this is necessarily like a useful tool in data center networks. Like, probably not, right? Like, one very, I didn't actually say it, but it's kind of implicit, right? I'm definitely assuming that how I route my packets does not affect failures, does not affect congestion, does not affect what other people are doing, right? Because look, I'm doing remote surgery from Hopkins to California. That's a negligible fraction of all traffic from Hopkins to California, right? Like I'm just not worried about how I affect the congestion. Other people's congestion, right? I can take that into my notion of failure, right? If other people do so much that things happen, then that's in my notion of failure. But what I'm doing just doesn't affect anything. But if you're in that setting, then maybe you should think, maybe subgraphs. Maybe I actually don't need to think about paths. Right, so we kind of showed that you can get kind of, at least for this small network, which is, it's small, but it's not a toy network, right? LTN is an actual company, and they actually have clients, and this is now inside of LTN, and they're running this. So it's not totally a toy thing. You can get very good performance for very cheap. The theory problem is the shallow light Steiner network problem, more or less. And this kind of failures at both is the hard case. Failures at one or the other, you can kind of solve that even in theory. Okay, so open questions, because it's always good to leave with open questions. Right, so we all have 15 minutes of discussion now. Like, if anyone has any ideas for other settings where this might be useful, I would love to hear them, right? Like I said, like at Hopkins, I wanted to be on the cool kids bandwagon and talk about medicine, so we were doing remote surgery. But, if you have other applications, that would be great. But if you do have other applications, is this, we came across this notion of like source faults, sink faults, and both, not kind of a priori, but by actually looking at this data that was happening. And it's not clear to me that that's generalizable to other settings. So whether it is or not, I would be very interested in hearing. An obvious open problem here, and this actually, if you want to think about it, this is what our AITF proposal was actually about. We just kind of couldn't really solve it, so we did this other thing, which ended up being a more useful system anyway. If I think of things as being stochastic, I think of my edges as failing with some probability, possibly independently, possibly correlated. Like, there's an obvious network design problem here, right? Which is find me the cheapest network that has at least some reliability. Or given a budget constraint, find me the most reliable you can get within that budget constraint. Okay, but like as has been pointed out, this even computing the reliability is a sharp p-hard problem. You say, fine, I can approximate it well by repeating a bunch of times, taking the sample average approximation. Okay, I still have no idea how to solve this network design problem. So if anyone has any ideas, I think that would be super interesting. Good. More theory. I really actually like this question of, like, what is the effect of the demand graph on problems, right? So it's very common in theory to have these algorithmic problems, and we say, oh, on planar graphs, they're easy. On bounded tree width graphs, they're easy. On blah, blah, blah graphs, they're easy. But then when we talk about the demands, we say, oh, maybe my demands are like structured, right? They're a star. Or they're totally general. And those are the two extremes I look at. But like, what about other things? What if my demand graph is planar? Not my actual graph I'm working on, but my demands. So actually, Chandra Chakuri has a really nice result about, I forget exactly what problem, but some cut problem when your demand graph is planar. And I think this is like really interesting algorithmic question in general. OK, so I'll stop there. Thanks.
What's a redundant single path?
This is a good question. I'm pretty sure what this is that it's a single path where for every edge, you've kind of calculated a replacement path, like in case that edge fails.
Oh, just for each edge.
Yeah.
The question that we have is, if multiple users try to use the network, how would that work?
Right. So, OK. I would say, I don't know if there's a problem with multiple users. The problem is if there's enough users that they themselves kind of cause congestion. Right? Like if 5 users want to do this, like fine, right? Who cares? It's not like that's massively different. But there's definitely this, this implicit assumption that, like I said, what you do doesn't affect the congestion anywhere. When that's not true, if you have like an enormous number of people doing this so that together they use up an enormous amount of capacity at these links, then yeah, you're gonna have to do something else. I don't know, not this. I don't know. You'd have to reason about that separately.
Then this boils down to the what we have shared resource problem. So that's
what?
it. That goes back to the shared resource problem.
Yeah, absolutely. So yeah, I mean, one thing that right, that's a good way of phrasing it, right? That like we heard about this kind of resource allocation thing. This is kind of not a resource allocation problem, right? Like there just isn't contention among edges in the way that we formulated it. But if you have that, then things are going to be different, definitely.
So the question that when we are considering fixed bound of the latency, why are we not considering queuing delay here? For example, when a source can have, suppose, large number of neighbors and destination has very few neighbors, then there might be incast happening somewhere in the network.
Yeah, so I feel like I've already said this a couple times today, that like things I should know more about that I don't know much about, and like queuing theory is one of them. I don't know much queuing theory, but the whole approach here is that the time constraint is so small that I can't do things like recovery, right? So in fact, if you have like non-negligible queues, I bet you're already dead. Like I'm pretty sure what this is kind of doing is assuming that I'm not operating at capacity on these links, right? Because if I'm running an overlay, I've paid AT&T to guarantee my 5 nines, with some latency bound. I don't need to now worry about that, right? AT&T takes care of it. And so, I think if you have queues that actually legitimately back up, that's going to be a problem also. But we certainly did not model that. Yeah.
So it wasn't entirely clear to us whether you were assuming that the overlay links were physically independent of one another, or whether they are correlated. It's they make share physical links, and to what extent are you accommodating for that?
Yeah, I mean, so I think the answer is like we are and we aren't, right? We aren't in the sense that So we are in the sense that when we do, for example, as was asked earlier, with disjoint paths, like they're disjoint on the overlay. They very well might not be disjoint in the underlying graph, right? And they just might not be. So in some sense, like we are not taking that into account, right? And I think it's pretty reasonable to say maybe we should take that into account. On the other hand, we arrived at this kind of realization that these are the kinds of failures that happen by like looking at data, right? We didn't invent this. Like I said, we started off with this stochastic problem before we kind of realized that that was too hard, and we went looking in the data for a nice characterization. So if this was a real concern, then you would hope that we would have like seen this, and this would have shown up in some way that wasn't a failure at the source or failure at the sink or failure at both, right? Since we didn't see that as a kind of as a failure mode that happened often enough to show up in the data, I'm not too concerned about it. Yeah.
Your cost model here appears, from what you're saying here, to be based purely on just the data that I actually transmit.
Yeah.
Because the overlay network must be built with a very high level of redundancy in it to enable some of your characteristics. So there's a base cost, the cost that the overlay network's not factored in here.
Yeah, so again, something I don't know much about that I should know more about is the economics of actually like networking. As a theory person, I've mostly managed to avoid economics. It's from what Yair and what the LTN people tell me, they certainly they pay something up front, absolutely, but the majority of their cost, or the dominator of their cost is this kind of, they pay something per packet, and that's how much things cost. So at least it's not clear that that's true of like every possible overlay you might make for every possible use case, right? But for like video streaming or remote surgery on the LTN network, that seems to be how the economics work. Yeah.
If I have a budget of 1.5 times the cost of single path, can I get any improvement at all over a single path, either in theory or in practice?
Yeah, good question. I don't know. I mean, we didn't try. I mean, presumably you could try to create a dissemination graph that lived within that budget, and that would be better than 2 disjoint, right? You don't have the budget for 2 disjoint paths, right? So you could say, well, if I have the budget for 1.5 times a single path, what's the best dissemination graph I could do? You would look at your kind of graph, look at your kind of failure data, and see if you could optimize that. It's a good question. I don't know the answer. Yeah.
Do you consider coding, like erasure correcting coding, for example, fountain code? So you send like 5 packets and you encode them in 10, so any 5 you get, you still can recover.
Right. So there is stuff in the paper about how to combine this with kind of some coding techniques. And in fact, we do combine this with some kind of basic coding techniques. But again, like the really harsh latency delay means that you can do basic coding things, but you can't do like super advanced coding tricks. Right? So in fact, for the video conferencing setting, they do like really advanced coding tricks, and they do really kind of advanced video specialized recovery on links, and we just don't have the time to be doing all of that. But you can certainly use some basic coding tricks to help. Yeah.
Were you able to model any of these numbers with your theory?
Model these numbers with the theory. No, so yeah, I guess okay, so if I understand your question, what you're saying is, look, like in this setting, like you could imagine proving a theorem which says that, for this class of graphs, there always exist dissemination graphs that are at most 2 times the cost that get this kind of reliability, right? We definitely did not prove such theorems, right? We looked at this optimization question of, given this graph, can I find the right dissemination graph? Not this question, not this like existential question of, do good dissemination graphs exist? That's an interesting question. As some of you know here, like my real specialty is on these graph spanner problems, and that's like the thing, that's what you prove about spanners usually. So I'd be very interested in such existential theorems.
I mean, just going to throw out something, since you're shopping for applications, I'm going to throw out a few random ones. None of them actually stick. So one thing actually, I think things like that, Siri and Alexa and so on, these days actually using multi-path TCP for reliability. And that's kind of the provenance of the what happens when a billion people use it question. Right? So I think they're actually using multi-path reliability and so on and so forth. So I think that could be an interesting application. Also, the other sort of big area where SDN has actually taken off is SD-WANs, software-defined WANs. Basically, it's like a fancy way of saying like sort of traffic engineering at the edge. Okay. So you get from your like different edge locations. If I have like Cornell, New York and Cornell, Ithaca, how do I sort of route between them? So I wonder if that, that's a very sort of niche application, but that's probably like one sort of where the money is in SDN right now.
Yeah.
So if you're like shopping around for applications, that would be something to look for. I guess the other question I would say is, I mean, maybe this is not a question, but something to look at is, based on your failure model, it seems like what you're really getting is multi-homing and not really overlay routing. And in fact, there's been like measurement papers looking at the benefit of overlay routing versus just multi-homing, which is like I just buy 2 links from 2 different ISPs and at my edge, and that's it. And I just load balance across them. And it could very well be the case that the results you're seeing, the benefits you're seeing are actually from multi-homing and not from the fancy overlay. And it might be useful to sort of show scenarios where you're actually getting benefit from the overlay, not just simple multi-homing.
So I don't want to make any claims that are false. I want to be a little careful. But what I think is true, and we talk about it in the paper, is that, and if you look at the pictures that I had, I didn't really talk about this, but things were color-coded. Yeah, this one, right? Like these color codes really actually correspond to like multi-homing, right? There's the green and the red, and the green and the blue and the red. And I don't want to say we did. I think we did, looking at kind of the benefit of like just multi-homing. And this kind of, and that helped. I mean, it definitely helped. But there were definitely enough cases of this stuff going wrong at the source that wasn't just handled by multi-homing, that we needed something else, that we needed more stuff for.
Okay, let's thank Mike again.